rotates counterclockwise, and a left-hand cutter rotates clockwise. Rake angles in milling cutters are determined by the cutter body and by the insert. Two rake angles, the radial rake and the axial rake, are determined by the position of the insert pockets in the cutter body. The radial rake is the angle measured between the insert face and a radial line drawn from the cutter axis to the cutting edge, hence the name radial rake. If the insert tilts toward the chip gullet, it has a positive radial rake. If the insert tilts away from the chip gullet, it has a negative radial rake. The axial rake is the angle measured between the insert face and an axial line or plane, and it may also be positive or negative. The combination of axial and radial rake angles yield three geometries of milling cutters: negative radial and axial, which offers the strongest edges but generate the greatest cutting forces; positive radial and axial, which provides the freest cutting; and negative radial, positive axial, which presents a strong edge to the work but pulls the chip up. The rake angle on the face milling cutter inserts, in conjunction with the cutter body's radial and axial rake angles, contributes to the cutter's effective rake. The cutter's lead angle influences cutting forces and chip thickness. The greater the lead angle, the greater the axial force, and the longer but thinner the chip. Standard milling cutters come in 0, 15, 30, and 45-degree lead angles. Most face mills are designed with insert pockets that are fixed. Other cutters are modular and accept a variety of interchangeable insert cartridges that hold various insert designs and seat the inserts at different angles. This allows the orientation of the inserts to be varied using the same cutter body. The pitch of a milling cutter is determined by the number of inserts in relation to the cutter diameter and can be defined as the distance from a point on one edge to the same point on the next edge. The coarser the pitch, the larger the chip gullet. Gullet size is important in face milling, since the chips are generally confined to the gullet until the insert exits the cut. Cutters may be coarse pitch, fine pitch, or extra fine pitch. Fine pitch cutters are used primarily for milling cast iron or for finishing work. Coarse pitch cutters provide a large gullet space necessary for milling ductile materials or in wide cuts. They are chosen for everyday work. Milling inserts are available with various grades and shapes. In addition, milling inserts have their own corner geometries, including the radius and the wiper flat. A large corner radius produces a finer finish than a small radius, but a corner wiper flat on the insert produces the finest surface finish. Sometimes a single wiper insert in a cutter will improve the surface finish, even if all the others are roughing inserts. For best surface finish and longest tool life, all inserts must be preset to carry an equal load. One or two inserts protruding further than the others will carry the cutting load and wear out prematurely. To hold close tolerances in milling, a very stable mounting is essential. There are several methods of mounting face milling cutters. Milling cutters under 3 inches in diameter are usually integral shank cutters. Face mills between 3 and 8 inches in diameter are mounted onto an adapter and go into the spindle. Face mills from 8 inches diameter and up may mount directly to the spindle. As an introduction, we've covered only a few of the many aspects of milling with carbide tools. Extensive calculations are also involved when choosing effective cutter types, cutter paths, and cutting parameters. Let's re-examine the material contained in this videotape. Cutting tools cut with an edge, and those edges can be described by their geometry. For metal cutting efficiency, it is critical to select the edge that cuts best, given the material and cutting conditions. The purpose of the edge and its geometry is to create a chip. The right geometry creates chips cleanly and efficiently. The wrong geometry may not cut at all, or cut poorly, fail prematurely, or damage the workpiece surface. Cutting tools fall into two broad classes: single point and multi-point tools. Turning uses single point cutting tools, usually coated indexable carbide inserts. Selecting turning inserts involves choices of insert grade, geometry, and tool holder design. The geometry of an insert includes its shape, relief or clearance angle, tolerance, type, its inscribed circle or IC size, thickness, nose radius, and the insert's chip breaker design. The largest influence on chip flow in turning is the top or back rake angle. This is the angle created by the top of the cutting tool and an imaginary line drawn horizontally through the workpiece diameter. A positive rake cuts freely. A negative rake is stronger but generates more force in cutting. The tool nose radius helps determine insert strength as well as workpiece surface finish. Insert size is designated by its inscribed circle, and the inscribed circle size of the insert must match the pocket size of the tool holder. In turning, making a chip is only half the battle. The other half is effectively breaking the chip with the right chip breakers and operating parameters. Tool holders and boring bars may be designated by their shank size, hand of the tool, method of clamping, insert shape, insert size, insert style, and rake angle. Multi-point tools rotate to cut. Face milling cutters are a type of multi-point tool. Face milling cutters vary in diameter, hand of cut, geometry, pitch, insert pocket design, and mounting method. The two rake angles determined by face milling cutter bodies are the radial rake and the axial rake. These two may combine in three ways for three different geometries of face mills: negative radial and axial, positive radial and axial, and negative radial, positive axial. Face mills may be coarse pitch, fine pitch, or extra fine pitch, depending on the number of inserts relative to the tool's diameter. The coarser the pitch, the larger the gullet size. Milling inserts with a large corner radius or a wiper flat provide a fine surface finish. In machining is to achieve the most efficient separation of chips from the metal workpiece. The edges of the cutting tool, driven by the power of the machine tool into the workpiece, forces grains of the metal to move away from the advancing cutting edge. This displacement causes the metal to fail. A chip forms along this line of failed metal, which separates from the work material. How that material failure and chip formation takes place is influenced by the work material, the tool material, the tool geometry, the forces applied by the machine tool, and various conditions in the process, such as heat and vibration. An efficient cutting tool geometry is one that minimizes heat in the cut and achieves a cool, properly formed, manageable chip while cutting the given workpiece material. Using the wrong cutting tools for a given operation may cause the tool to not cut at all, wear the tool out too quickly, break the tool, damage a workpiece, or fail in other ways. Before final selection of a cutting tool can be made, certain process parameters must be known, such as the composition and hardness of the workpiece, its shape and surface condition, the machine's horsepower, the machine's feed and speed capability, and the rigidity and security of the work-holding method. All these variables factor into the selection of tool shape, tool material, and machining process parameters. Nearly all turning uses single-point cutting tools, that is, tools that cut in a single cutting edge. Most turning today is done with coated indexable carbide inserts, but the tool material may also be high-speed steel, brazed carbide, or inserts of ceramic, cubic boron nitride, or polycrystalline diamond. Several decisions are required when choosing tools for turning, including the selection of the material or grade, the geometry, and the tool holder design. Just a few basic geometries and carbide grades are used in 75% of turning applications. Tooling decisions for lathe operations